complex behaviors that are difficult to find by random chance can be found using incremental fitness functions, which change the fitness function used to evaluate a robot over evolutionary time to develop simpler sub-behaviors that should add up to the complex behavior at the end. When to switch between these different fitness functions has typically been hand-coded by designers, and if done well leads to success, but if done poorly leads to the robot equivalent of a student stressing over finals that they haven't studied for. My two main points of inspiration for this is the work by Hess et al. At Google DeepMind, where they changed the environment around a robot to achieve robust behavior, and Josh Bongard's work, where the morphology of a robot was changed over time in order to increase the robustness of the behavior, particularly the phototaxis, and a comment in the paper about how evolving for too long within certain behavior frames led to poor fitness overall was interesting. So my problem was to minimize the number of steps within the bullet simulator for the table robot from our homework to get within 1 unit of a randomly placed goal that was 20 units away from the starting position. For this, I came up with two sorts of switching parameters, one that was proportional to the evolutionary time of the robots, or switching parameters that were based upon a proportion of a reference fitness for each sub-fitness function. And these sub-fitness functions were either to minimize the angular direction of the robot at each time step from the direction to the goal, or to minimize the average distance of the robot from the goal at each time step. These solutions wound up being 2-entry vectors of doubles that were bounded between 0 and 1. The step switching also had the additional boundary condition that the second entry had to be greater than the first. The reference fitnesses that were used were value that corresponded to an angular variation of about 5 degrees, about 5.7, and reference 2 corresponded to the robot being a 1 unit away from the goal on average. So what I actually wanted to use was CMAES to evolve the hyperparameters, a parent population of 5, a combined population of 10, and evolve that for 2,000 time steps. And in a loop inside of that, I want to use a population-based method developed in class to evolve the robot's behavior with a parent population of 10 and a combined population of 20, evolve for a max of 1,000 time steps, and generalize that behavior over 10 robots. What I was actually able to use was only evolve for 100 time step using a population-based method for the hyperparameters, and for the robot I was only able to evolve for a max of 400 time steps and generalize over 3 robots. Because I couldn't use the CMAS, I had to use a different mutation scheme that was multiplying by a step size 0.4 and a number chosen from the randouble function provided by Yoast. Here's some of the results, which basically show not much variation over time, in that both solutions converge to basically about 610 steps within the bullet simulator for the robots. As we can see with the best solutions, that they don't really change much over time, and both tend to just maximize the amount of evolutionary time used to evolve under minimizing the distance from the goal. So I think my project definitely could have benefited from looking at the details more, as I spent 2 weeks trying to evolve the robot to find a goal that was above or below the ground rather than on the XZ plane, and also would have also benefited from being able to formulate a more difficult problem than find a goal, something like balancing a box on top, and finding a goal then would have been slightly unrelated fitness functions that would have also led to more interesting behavior overall. Thank you for your time.